Picture the hottest afternoon of the year. One water system feeds a neighborhood, a hospital, and a new AI data center. At 4:17, demand is climbing everywhere. Inside the data center, thousands of processors are turning electricity into heat. Fans push it away from the chips. Pumps carry it through the building. On some campuses, cooling towers release it by throwing water into the sky as vapor. That water will not return to the tap tonight. From the road, the building looks asleep. No smoke, few windows. Behind the walls, the cooling system is working every second. Now the town has a question nobody asked when the permits were signed. Who gets priority? AI has not emptied America's reservoirs. A facility can look manageable in a national report and still pressure the wrong water system during the worst week of summer. The cloud has an address. That address has a pipe, and the fight over that pipe has already begun. Subscribe to Black Box Atlas. We follow the hidden systems shaping the future, especially the parts companies leave out of the presentation. A server does not need a drink. Its heat does. Electricity enters the machine and ends up almost entirely as heat. Dense AI. Racks make that heat harder to remove. Some data centers use outside air. Some circulate liquid through sealed pipes. Others use cooling towers, where water evaporates and carries the heat away. Evaporation is effective, but consumes water locally. Cooling towers also need blowdown to remove concentrated minerals. One universal number for AI water use is useless: a cold weather facility. With a closed loop behaves differently from an evaporatively cooled campus in a dry region. Density, humidity, electricity, and water source change the result. Direct-to-chip cooling can move heat through liquids sealed inside the system. Immersion cooling can surround hardware with a specialized fluid. Both can reduce on-site evaporation, although their equipment and electricity still carry an environmental cost. The plumbing decides whether a data center becomes a good neighbor or a very expensive problem. Northern Virginia became a digital capital before water entered the conversation. Fiber routes converged there. Developers found reliable power, land, and tax incentives. Every new facility made the next easier to justify. The region became Data Center Alley. Then AI pushed more computing power into each rack. Virginia's Legislative Research Agency found that data center water use was sustainable at the time of its review. Many facilities used no more water than a large office building. That reassuring average hit a smaller group of heavy users. Most campuses buy from utilities connected to rivers, reservoirs, or groundwater. Oversight becomes weaker when a locality divides that supply among homes, farms, industry, and new development. In Eastern Virginia, groundwater is already supporting all four. A 2026 study, reported after a public records request warned that parts of the region could struggle to supply a large new facility using direct evaporative cooling. Virginia began moving towards stronger requirements in pressured areas. New projects may need air cooling, closed loops, reclaimed water, or stormwater reuse. Virginia is not running dry. It is discovering that a data center cannot be approved like an ordinary warehouse. The dangerous number is often the peak. Summer demand nobody sees until the building is already running. Technology companies know water has become a business risk. Their reports now contain efficiency targets and restoration projects. Google reported replenishing 4.5 billion gallons in 2024. That was equal to 64% of the fresh water it consumed that year. Amazon reported that its data center fleet withdrew 9.4 billion liters in 2025. It said it had reached 75% of its 2030 water-positive goal. Microsoft said roughly 90% of its owned fleet used low to zero water cooling. Its newer closed-loop design uses no water evaporation during operation. These improvements matter, so do the words. Withdrawal is water taken from a source. Consumption is the portion not immediately returned, often because it evaporates. Replenishment funds projects, intended to restore or save water. Those numbers cannot be swapped. A wetland restored over a year does not create extra water when a cooling system reaches peak demand. A project elsewhere cannot raise a local well. Residents need a simpler disclosure: which facility, Which water source? Which cooling system? And how much water during the hottest month? The engineering is becoming more sophisticated. Public visibility is still trying to catch up. This conflict is avoidable. Developers can avoid stressed aquifers. Cooling systems can use reclaimed wastewater. Closed loops can carry heat without continuous evaporation. Operators can use outside air when weather allows. Utilities can demand peak use estimates before approving connections. Governments can require drought plans. Communities can insist on independent measurements instead of annual promises. Every solution costs money. Air cooling can use more electricity. Closed loops require specialized equipment. Reclaimed water needs treatment and separate pipes. Moving away from a network hub raises costs. Those costs belong in the price of AI. Before construction, the public should know the water source, summer demand, likely consumption, verification method, and what happens when supply falls. Hospitals, farms, chip factories, and power stations need water. AI's defining. Pressure is speed. Towns are approving enormous infrastructure while its future. Scale remains uncertain. The next AI race runs through chips, electricity, and water. The winners will build machines that think at extraordinary scale without, forcing the communities around them to wonder what will come out of the tap. Subscribe to Black Box Atlas for the stories hiding behind the technology.